Good evening, everyone, and welcome to Deep Talks. I'm Constance Walter. I'm the Communications Director with Sanford Underground Research Facility, and I'll be your host tonight. To make the most of tonight's experience, take a minute to prepare yourself. Grab a mug of your favorite hot beverage and collect the following items: a plastic or wood cutting board, a metal pan or tray, ice cubes. Okay. Now, tonight's event is sponsored by Crow Peak Brewing Company, RCS Construction, Northern Hills Federal Credit Union, and Chuck and Jolene Lichtenwallner. We thank them for their generous gifts and continuing support of science outreach and education. Crow Peak Brewing Company is also sponsoring tonight's door prizes. And we have 3 prizes tonight: a growler with 1 fill, a 6-pack of Crow Peak's locally brewed craft beer, and a gift certificate with a Crow Peak t-shirt. The poll you're seeing on your screen is only available to our Zoom webinar viewers. So if you're watching on Facebook, remember to join us next time on Zoom so you have a chance to win. To enter to win this prize, you must be 21 years of age or older, and you must be able to pick up the door prize at Crow Peak Brewing Company in Spearfish, South Dakota. If you are joining us via Zoom webinar, please select the option to enter yourself. We will randomly select a winner at the end of the event and contact our winners via email. Now, tonight, as always, we would love to hear your questions. If you're joining us through Zoom, please use the Q&A function to submit questions. If you're watching live on Facebook, add your questions to the comments section. If you participate in the polls that are asked throughout the presentation on Zoom and Facebook, you'll be entered to win some really cool surf branded swag. Tonight's presentation is brought to us by the letters E&O, as in education and outreach, and the number 5, as in the number of fantastic E&O team members who will be presenting tonight. And those 5 team members are Nicole Reiner, Peggy Norris, Julie Dahl, Ashley Armstrong, and Chad Ronish. Please welcome the amazing education and outreach team.
Just like a magic trick. Okay, so we know that some people love winter. We also know that some people can't wait for it to end. But for our E&O team, the best part about winter is thinking about heat. And with Valentine's Day right around the corner, our love of science.
So let's begin tonight by thinking about heat. Hopefully you have a mug of something hot nearby to inspire you. What is heat? Take a moment on your own to think about how you might answer this. Share your responses in the chat. Okay, we have a response that says flow of energy. Another temperature value.
I think these are our kind of people.
I like it. So at the most basic, heat is a form of energy called thermal energy. Thermal energy is the energy something has because of the movement of its molecules and atoms. As molecules heat up, they move faster. And the faster they move, the more their thermal energy increases.
So the transfer of thermal energy is also moving from one object to another?
Yeah. You might notice that we have that what we are touching has an effect on some items. So I want you to think about how that heat is transferring in that warm cup that we have with us tonight. So go ahead and hang on to it. What do you notice, Julie?
Well, I guess one of the things that I notice is that my spoon is warmer than my mug.
Ah. Okay, so you might also notice that some heat might have transferred to your hands when you picked it up. And I actually felt the table below my mug and was able to tell that the table was a little bit warmer in that area. So the next question, do all objects and materials respond to heat in the same way? Think of an example to help support your answer when you're thinking about this. Go ahead and share your thinking to somebody who's in the room with you, or if you're willing, share it in the chat. A response that says all materials conduct energy differently.
Well, this is going to be a good chance to check that out because we have a couple different materials here with us today.
I like that. So I want to give an example. So imagine it's a hot summer day. I dream about that this time of year. So we're at the park. We have a few options of where to sit. We could sit on some rubber swings. We could sit on a wooden teeter-totter. We could sit in the grass, or maybe on the metal park bench. What would you choose, Julie?
Grass makes me itchy, so I might sit on the swing.
You know what? I was thinking I would choose the grass because the grass always feels a little cooler to me. So let's take a look at the materials that we rounded up tonight. So we have a cutting board and a metal pan of some sort. So what do you notice about each of these objects?
Well, I think I notice a couple different things. One of the things that I notice is one of them feels heavier than the other.
Okay.
But I also noticed when I put my hands on them, they felt different. One felt cooler than the other one.
So let's take a few minutes to have a quick investigation. In a moment, you'll be asked to place one ice cube on each of these objects at the same time. But before you do that, I want to make some predictions about what we think might happen or what we would expect. So what do you expect will happen and why? We actually have a poll question here and we'd love for you to respond in chat. So your options are A, nothing. B, the ice will melt at the same time quickly. C, the ice will melt at the same time but slowly. D, the ice will melt first on the cutting board. Or E, the ice will melt first on the pan. So I'd first like to see what everyone in the audience thinks as they put their predictions into the chat. All right, well, it looks like we're getting a mix of reviews in the chat from our two different platforms. So let's give it a try.
I'm so excited. Are you ready?
I'm ready. This is going to be good.
At the same time, right?
At the exact same time. You can try this at home too. So we aren't going to have to wait long. I'm already seeing some differences in the results here.
That is not what I expected.
Huh. There are some mixed views out in the audience as well. So many of you shared that perhaps the cutting board was going to melt the ice faster. That's not what's happening here.
No.
Let's investigate.
Maybe we should talk about the why. So we know that when we put our hands on it, what we feel doesn't reflect what we saw. That cutting board felt warmer to me when I put my hands on it. And I thought for sure that we might see ice melt on there first. Now, that's by touch. It doesn't really have a number on it, so I'm curious. If we take the temperature,
Yeah, let's
what are
see.
we gonna get it?
70.5 on the wooden cutting board. And 70.5 on the metal sheet pan.
And I guess what my fingers were telling me doesn't quite line up with that. But it does make sense if I think about it, because both of these were sitting out while they were waiting
Right.
for us to start our presentation. So they've been sitting in the same room at the same temperature for quite some time. Now, there's some science behind that we should think about. So heat versus temperature. We talk about those things together all the time.
Yep.
We use those terms, and we probably don't think very much about that. We know that heat is a form of energy. You told us that, right? But temperature is actually the measure of that energy. So
Right.
the temperature is how much thermal energy is available. Both of those happen to have the same available thermal energy. And when we think about that, we think about the flow of heat.
Okay, so heat is the transfer of thermal energy from one object to another.
Right, and in this case, we're thinking about the object to the ice cube,
Okay.
okay? So when we talk about heat flowing, we talk about how it moves from place to place. And in science, we're lucky because we know that heat moves in predictable ways.
Right.
It's going to move from a high value to a low value, okay? And in that flow, it's always trying to reach equilibrium. It wants those temperatures to equal out. So we know in science that when we put those ice cubes on no matter what surface, that eventually we're going to end up with a small puddle of room temperature water.
Right, so even though this one doesn't seem to be doing much now, eventually the ice cube on the wooden cutting board is gonna look just like the ice cube on that metal pan.
Right, so let's put this into context. Think about your hot mug right now. Okay, we know that if you leave that out, eventually that mug is going to cool down,
Yeah,
but it'll never be cooler than the temperature of this room.
true.
Okay, the same is true if you think to your summer hopes and dreams. Okay, if you had an icy beverage instead, that ice would melt and it would eventually warm up, but it would never get warmer than the space that it was sitting in.
I always just think of it on that 98-degree day. I get a 98-degree drink.
Yeah, equilibrium.
Awesome, yeah.
Okay, so if we take that same concept here, we know there has to be at least one more component at play, right? We felt that that cutting board was warm.
Right.
But what made us feel that? Okay, if you put your hand on there, where is the heat flowing?
Well, I feel like heat's probably flowing from my hands to the items.
Okay, so when we put the ice cube on there, where is the heat flowing?
Ah, heat's probably flowing in the opposite direction.
Right, from the item to the ice
To
cube.
the ice
right?
cube, yep.
But what's curious about this is that one of these happened really quickly, the other not so quickly.
Right.
Okay, so what do you think caused that difference? It's not what we expected.
Right. So, I don't know, can you explain that a bit more?
Well, something felt different when you touched that pan. And we know that the sensation of cold is telling us something. So each of these objects is made from a different material.
Right.
And some materials, have you heard of insulators and conductors?
Yeah.
Okay, so some materials will insulate and some will conduct. What do you think we have going on here?
All right, so we have an insulator and we have a conductor.
So if we add that to the mix, we know that with this ice cube investigation, okay, it melted quickly. So we know that transfer was happening more quickly on the conductor.
The conductor, yeah.
Okay, what about the insulation?
It's keeping that flow from happening.
Right?
As
It's
quickly.
happening slowly,
Yeah.
right? So we don't notice that. So this brings me back to my childhood. Growing up, a million times I heard my mother say to me, "Close that door, you're going to let the cold in." So I want to put up a poll. I'm not sure. We all probably heard something different growing up.
Yep.
But there are two options on there. We're looking to find out which one you think is the most scientifically correct. So you could choose A, shut the front door, you're letting all the cold air in. Or B, shut the front door, we aren't paying to heat the outdoors.
I think I've heard them both.
Yeah, but which one is most scientifically accurate?
Let's see if the audience says.
All right, let's hear what they have to say. Is our audience saying anything? All right. I'm so excited.
I'm excited to see what they think is right now after this little lesson.
We are ready. Oh, overwhelmingly 85% say B, we're not paying to heat the outdoors. Now, if you're watching, Mom, I'm sorry. Growing up, you always told me not to let the cold air in, but that's not how the science works.
Yep, the audience was correct.
You guys rock. So what we're going to do is we're going to transition to Chad, who is going to walk you through our next bit of cool science.
Well, hi there. I have my drink in an insulated mug so that I can't tell whether it's hot or cold from feeling the outside, but it just stays whatever temperature it's going to stay inside the mug. So a favorite science activity that is reserved for only the coldest parts of wintertime is walking outside when it's way below zero, taking a container of hot boiling water, throwing it into the air, and letting it turn itself into snow before it can hit the ground. So that's one of the ones I like to do. Cold water won't do the same thing. If you take a container of cold water, you throw that up into the air on that same really cold day, it's just going to splash to the ground like water. So it's not going to do the same thing. In fact, for the best effect with this, you want to have the boiling water above 200 degrees Fahrenheit, and your air temperature has to be minus 10 degrees Fahrenheit or colder. Go ahead and play that video. And so what you see is that boiling water going up into the air and the little streamers of snow coming down as it comes down to the ground. So that's going to take us to our first poll question. It's actually our only poll question. I want to know what you think about this. Why would boiling water work better at making snow than using cold water to make snow? And I'm going to help you out. I'm going to give you three choices. One, boiling water is close to steam, steam is close to water vapor, and that makes snow. So that's your first choice. B, heat flows from hot to cold better than it does from cold to cold. So it's that heat temperature difference that's going to make a difference. And C would be boiling water has bubbles in it. That increases the surface area, which increases the heat flow. So those three choices. Go ahead and enter your answer in the chat or in the poll selection on the Zoom. So I'm not going to tell you the answer because I want you to think about your answer as we go through the rest of this discussion. Because I'm going to talk to you a little bit about the science behind it and a little bit about how this happens in other places. So first thing I want to talk to you about are states of matter. So matter exists naturally in three states if we ignore plasmas at the top end. The amount of energy in the matter determines the state of the matter by changing the particle motion. So solids have a slower particle motion than liquids, which have a greater particle motion, and then vapors have the most particle motion. What happens when you boil water is you're adding energy to liquid, which cause those particles to move faster, and then they end up spreading themselves out and filling up their container a little bit bigger. They increase their spacing because of the amount of energy in them. When you throw boiling water into the air, the hot water forms in hot water droplets. Those water droplets are spread out now because we threw it into the air, which got all the water moving even more. And they're so hot that those tiny little water droplets then the air can't hold all of that heat energy. And so they immediately condense back to liquid. And since they're so small and it's so cold, all of that heat energy that is in each little water droplet can then move to the air, flow right out of it, and form itself a solid or a little ice crystal. Extremely cold temperatures quickly freeze those water droplets, and that is our snow making. So think about your answers to that poll question, and does your answer support the fact that it's the little teeny particles being able to transfer their energy out that helps cause that phenomenon? You could say that making snow is really just making really, really small ice crystals. It's more like frost that you would get out in a meadow than it is actually snow that would fall from the sky. Got questions? No, we're just kidding. We got energy. People are digging. We're having fun. Okay. So next image here, I want to show you, this is a phenomenon that happened just a few weeks ago on the way right here down below the lab. So the Surf wastewater treatment plant has an effluent discharge. It comes down in a waterfall, and it's just this really nice 70-degree temperature. And so it stays nice, the same temperature all year long. Well, that morning it was so cold, it was about minus 15 degrees, that the water vapor coming up from the waterfall formed ice crystals and frosted the whole valley. And so one of the communications team, Erin, got this picture on her way to work that day, and it was just a really interesting phenomenon due to that same process that was allowing us to make our snow. So, if you've been watching the Olympics, you may have heard that in Beijing there isn't a lot of snow, and so they're using man-made snow for all the events, or for a good number of the events. Many of the contestants aren't real happy about that because the man-made snow behaves differently than natural snow, and for their competition they want the best. Here in the Black Hills at our ski resorts, we also are making snow for the skiers around here because we just haven't had the snowfall this year. So I want to talk a little bit about how we make snow for a ski mountain. For our boiling water, we talked about heating that water up to increase that surface area. It wouldn't be plausible for us to go ahead and boil all the water that we're then going to shoot up on that mountain to make snow. It would be incredibly cost prohibitive. So instead of heating the water, all we're going to do to make our snow on our mountains is we're going to use water, cold air, just less than 28 degrees Fahrenheit, and an air compressor with a nozzle that can create a mist. The air compressor is what becomes the key here. The compressed air adds energy to the water that forces the molecules to move apart into their own little spots again, almost like a water vapor. We then push that water out through a spray nozzle that sprays it around, spreading it out even further. With that high amount of energy and that really, really small particles, we've again created really, really small drops of water vapor that can change back to a liquid and can then drop right back down and form an ice crystal and fall to the ground as snow. Now, it's ice crystals, it's not snowflakes. Snowflakes behave a little bit differently. Snowflakes grow as water crystals add themselves to one initial ice crystal in the middle. So snowflakes grow from the inside out. And as they get bigger, they get that beautiful snowflake pattern that we all grew up knowing. If you look at the other picture, that's man-made snow. So man-made snow are little droplets of water, and on those droplets of water, they freeze from the outside in. And so it creates like a little snowball or a little snow ice crystal. So The key to making snow, whether you're talking about the boiling water challenge or if you're talking about putting snow on the mountains so that we can ski on them, is surface area. We have to create a lot of surface area so that our water can let its heat flow from the water particle out into the environment, and that's what's going to allow our ice crystal to form a solid. My teammate Ashley's going to come up now, and she's going to show you another example about the transfer of energy.
All right, we're going to start off by watching a short video clip. So I'll have them put that up. While you're watching this, I want you to pay attention to what's happening here. What do you notice? What do you wonder about what's happening? All right, so I'm going to give you a little bit of time to put your notices and wonders into the chat. Well, here's one that says, I wonder if the goalie has a fever. Is he sick?
There's one here about, is the goalie on fire?
Ooh, is the goalie on fire? That is a good question.
There's
Oh,
another one about how cold is the space that the goalie is in.
yeah. How cold is the space that the goalie is in? Is the goalie on fire? Does the goalie have a fever? These are some good notices and wonders. That it may not be the individual, but somebody thinks that the steam is possibly coming up behind this hockey goalie. So there's actually some science behind it. As one exercises, there can be a slight increase in body temperature, and it's a good practice to warm up and cool down when you're exercising. So this hockey goalie had time to warm up and adjust to the environment that he's playing in, and hopefully he also cooled down before leaving. An abrupt change in environmental temperature can be harmful to humans and to an individual. So as we talked about the flow of heat earlier with our cutting board, our pan, and the ice cubes, think about the flow of heat that you saw happening in this video. So as a personal example, my kids love to run out of the gym after winter sports practices without the proper winter attire. They're often annoyed by me telling them, put your hat on, zip up your coat, put some sweatpants on. But there's actually some science behind it. I'm gonna pass this off to Nicole.
All right. So I'm going to actually set up a little experiment here. So I have a mitten, and I'm going to put the thermometer, it's been in the mitten, but I'm going to keep it in the mitten, and then I'm going to put the same type of thermometer beside it. And I'm going to leave that sit there while we're talking for a little bit, and then after a little bit, we're going to actually do some comparing here. So there's a question that I think we need to think about here as we relate the science concepts and we think about heat flow. For our youngest learners, something that might be of interest to them, and also to those of us who are older, but gloves versus mittens. So I want you to think about when you go outside, it's really cold outside, what do you choose? Do you choose gloves or do you choose mittens? Or why? And why? So take a moment, put it in the chat. Which one do you choose and why? There might be a variety of answers, but we'll wait to see what some of the folks want to enter. I mean, there's lots of mittens and gloves that are out there. They have different types of fabrics. They have, they're made of, sometimes they have thinsulate, sometimes they have down. And we've had mittens and gloves around forever. I actually looked up a couple of history things about mittens and glove. Mittens, they think, have been around since the Ice Age based on some cave drawings. And gloves have been around, they found some actually in Tutankhamun's tomb when they went in to excavate or to look into it when they discovered it. So Gloves or mittens? Do we have some answers in the chat? Yes. Okay, so some folks are putting in that they would choose mittens because your fingers stay together and they can warm each other up. Although I know that there are some folks who might put in gloves as well, because a lot of times gloves allow you a little more dexterity. You have more use of your fingers. So we'll have some people on each end. But when we're thinking about transfer of heat, that might impact the decision you make. And actually, I think it might be wise to think about an expert in choosing gloves or mittens. So if we go to the next slide, we'll actually see a picture of someone I think would be someone we could definitely talk to and ask gloves versus mittens. And that would be Chloe Kim, who is a part of our U.S. Olympic snowboarding team. As a matter of fact, she won a gold medal last night. And if you look carefully at the picture, you will notice she has on one really big pair of mittens. And for snowboarding, of course, warmth would be very important. And dexterity, not as much. And so our snowboarders are wearing mittens. There's an interesting way to look at heat. And so one way to do it is to look at an actual infrared picture of someone with gloves and mittens on. So if you take a look at this picture that's showing right now, what you'll notice is that one hand has the glove and one hand has the mitten. And these are made of similar materials, so that's not going to change what the picture is. But you'll notice on the hand with the glove, there's a lot more red. And so what that's showing is heat, which means there is a movement of heat from the hand to the glove to the air. And the one with the mitten, you see more yellow, so that's cooler. So there's less movement of heat from the hand to the glove to the mitten, which means that there will be more heat retained inside of the mitten, which means your hands would stay warmer longer having those mittens on there. All right, so we're gonna move to this, back to this mitten here with the with the thermometers we have. And so they've been sitting here actually since the beginning of the deep talk. And so I've got two thermometers and I'm gonna look at both of them. And before we do that, although I want you to put in the chat, what do you think? We're going to ask a question, actually. What do you think is going to happen? So for a moment, before we actually check the results, let's look at the poll question that's going to go out to the group. So there are some options on the poll question. If we have this mitten with these two thermometers, one inside of the mitten, one on the table, do you think that A, the thermometer inside the mitten will have a lower temperature than the thermometer on the table? B, do you think the thermometer inside the mitten will have a higher temperature than the thermometer on the table? Or C, do you think the both of them will be the same? So take a moment and actually vote A, B, or C, whether you think A, the thermometer inside will be lower, B, the thermometer inside will be higher, or C, they're the same. This is a common question, actually, that comes up with our elementary school students. Our elementary school students really do believe, and as a matter of fact, our language says this, put on a warm sweater, grab your warm mittens. The language indicates that maybe the object that's warm is the sweater or the mitten. So did we get some poll answers in? Sure, or you could just tell me what most of the answers were. 58%? Go with C. Ooh, so just over half. This is good. C, let's see what happens. Okay, so I'm going to look at the one that's on the table, and it is at 23 degrees Celsius, which is about 72 or 73 degrees. I'm going to pull the one outside of the mitten and take a peek there too. Exactly the same, 23 degrees Celsius. Because, as I talked about earlier, everything is equalized to what the temperature in the room is. So the mitten actually isn't warm. What's warm is our hands that we put inside of the mitten, and they are actually what's creating the heat. So the mitten just helps us insulate and keep our fingers nice and warm in that pocket of heat inside and doesn't let it escape, doesn't let the heat escape. All right, so we've got one more poll question, actually. So we want to see if you can apply what you're learning with this next poll question. So the question itself is, why do your hands start to feel cold even if you have your gloves or mittens on when you go outside into the cold? So your options are this. A, the cold seeps in through the seams of the mittens or gloves. B, the heat seeps out through the seams of the mittens or gloves, or both A and B at the same time. So A, the cold seeps in, B, the heat seeps out, or C, both of those things are going on at the same time. So take a moment and vote A, B, or C, and then we'll take a look at how well we applied our understanding about how transfer of heat works. How are we doing, Matt? Did we get some answers on our poll? They're still coming in, all right. Ooh, overwhelming answer. Which one is overwhelming at this point? B, great. So we are paying attention and applying our knowledge. That is true. So the heat seeps in, but the cold does not, actually there is no such thing as cold, only the absence of heat. So way to apply your knowledge. So back to the original question that we had, gloves or mittens. And frankly, if you can't decide, you could just go with glittens. That's it for me, actually. So I'm going to pass it on to my colleague, Peggy, who's going to talk about how we really try and think about the science that's going on at SURF, and then how we relate that to the different ages of kids, K through 12, and think about the science concepts themselves. On to you, Peggy.
All right. All right. So my colleagues did a great job of introducing several concepts tonight: heat, temperature, thermal energy, and conductivity. Thank you. I can take this off. And they highlighted some common everyday applications of these concepts. They also highlighted some misconceptions that are very common. What I'm going to do is talk to you about how we take this into the classroom. So if I can have the first, I probably have the first slide, sorry. So we go into classrooms to do presentations, and instead of talking about everyday common applications, we talk about connections to Sanford Lab, the science and engineering that's being done here. And in this case, the concepts we talked about tonight, we are connecting to the EGS experiment and the SURF and the Sigma V, sorry, the EGS collaboration and the Sigma V experiment. So if you'll go to the next slide, Matt, thank you. So we have a variety of presentations we take to classrooms at all grade bands. This particular topic fits in very nicely with middle school science standards. And so we tie in to the Sigma V experiment and all these concepts of heat. So we go into the classroom with this presentation called Hot Rocks, Renewable Energy from the Earth. And we have the same phenomena that starts it out that you looked at tonight with the ice and how it melts differently. And the students always choose the block that feels colder, the warmer, as the one that's going to melt the ice. And they're always shocked when it's the other way around. So we're trying to work with them on their misconceptions too. So when we do these presentations, we have some standard slides about Sanford Underground Lab that we go through. And then in this particular presentation, we start with talking about natural geothermal energy. So I'm just going to be showing you in the next several slides, some slides that are straight from this presentation. So we look at pictures of sources of natural geothermal energy, geysers, fumaroles, which are steam vents, and hot springs. We have some pictures you might recognize if you've been to Yellowstone. We even have one from the Black Hills, a very old picture from Evans Plunge in Hot Springs. And we talk about what are the common ingredients of all these different forms of geothermal energy. And kids always get water, of course. They usually get heat. And the third one, if you'll change slides, please. The third one, they have a little harder time with. In these natural forms of geothermal energy, you need some kind of pathway that gets that hot water up to the surface. But if you have these, then you can use it for making power. And if you'll go to the next slide, this is a picture of the geysers near Sonoma, California. And this is the world's biggest geothermal power plant. And it makes about 0.3%, or overall geothermal energy is about 0.3% of the energy production in the United States. So what you learned about, if you were at Deep Talks last month, you learned about the EGS collaboration and how they are trying to make geothermal energy possible at locations that don't have these natural geothermal features by forcing water through the rock to pick up the heat and out. And if you want to learn more about that, then the Vimeo site for Sanford Lab has last month's Deep Talks. What I'm going to do is talk a little bit about the applications here to the Sigma V experiment at Sanford Lab. So this slide is the temperature as you go down in depth. And anybody who was down during homestake days knows that the rock was pretty hot. And especially people who got a chance to go all the way down to the 8,000 foot level where the rock temperature was 135 degrees. We always talk to our students when we give tours about how at the 4850 level, the rock temperature is naturally 95 degrees. The interesting thing is, if you look at this graph, it's a little hard to see. The top is the Fahrenheit, and the old data is showing where it was back during the mining days, it was 95 degrees. But when they went back in 2009, after they pumped all the water out, the rock temperature was 80 degrees. So it had dropped significantly because heat had transferred from the rock to the water while that level of the mine was underwater. So over the course of time since then, as we've built the science lab and we've done a lot of work on the 4850 level, we move a lot of air underground, it stayed pretty cool. And the Sigma V experimenters have found that in order to get back to where the rock temperature is 95 degrees, they have to go at least a meter into the rock mass to find that. Now, I'd like to talk about one more misconception that the students always have, and that's when we talk about the temperature as we go down into the mine. They always think it's because we're getting closer to the center of the earth, and that is not the case. We're still very much in the upper crust. But what is happening, as you heard at the beginning of the talk, heat is oh, thank you. We're going to look at this in just a second. Good. Heat is when the molecules and atoms inside material are moving faster, then you get a higher temperature. And so as the pressure of the weight of the mass, rock mass above the 4850 level pushes down, it's making those rocks move faster. And then we get higher temperature than we do at the surface. So as you go deeper, you have more weight, pushes more, your atoms move faster, you get a higher temperature. Okay, so I'm going to show you what we do, the experiment we do with the students that is a model for the Sigma V. So I'm just going to fill a couple cups with some water. and put thermometer in them. So we actually have some hot rocks from surf collected in the parking lot. And there's quite a variety. I don't know if it's possible to, I'll just pull out a couple of these. So we have some core samples. Here's a white one. And if I look at the temperature of it, it is hitting about 130 degrees Fahrenheit after sitting in this crock pot for a while. If I take another one, say let's take another sample. And it's reading more like 101 degrees Fahrenheit. So depending on where you are underground, the rock temperature, the rock material is going to conduct heat at different temperatures. And so what the students do is they see how much the water temperature goes up with their sample of rock. Then they compare with their other pairs and sees why different samples seem to have different temperatures, And so they do the same experiment that Sigma V is doing as they compare different kinds of rock underground to see which ones will transfer heat better for geothermal energy. So this is what we do with the students. We can go back to the slides. I just have a couple slides left here. So this is a picture of one of the boreholes. I think this picture was actually photographed by Matt, who's running the show here. And it shows one of the boreholes that are used for these experiments to get more than a meter in so that they can try to extract some heat from the hot rock inside. So if you go to the next picture, this is a diagram of the experiment when it was at the 4850 level, and the high pressure water was forced down that green borehole and then through rock and out the red borehole. So when we talk to students, we have models for the different boreholes, and we talk about how it's moving through fractures in the rocks and so forth. So that's the experiment as it is underground. And so to summarize, if you go to the last slide, we are taking all of these concepts that are part of the curriculum anyway and connecting them to directly to the experiments that are happening here at Sanford Lab. Now, before we take questions, I'd like to do one more thing. I've been here at the lab 13 years and have been going to Deep Talks since they started. And I'm sure many of you in the audience have been coming to Deep Talks, and we've talked a lot over the years. I'm retiring tomorrow, so this is my last one, but I hope to be in the audience in the future when we go back face to face. And in the process of thinking about a long career and retirement, I was thinking back to when I first got interested in science and in doing science and eventually in giving back into science education. And what I would like to do is thank two teachers whom I don't remember their names from Goddard Junior High School in Midland, Texas in 1967 and 68, 8th and 9th grade. These two teachers taught in a way that got everybody excited and passionate about, at least it got me excited and passionate about doing science. So and invite the rest of the team to come up.
I'd like to thank my teachers at Stanley County, my elementary teachers, my middle school teachers, Mr. Giddens, Mr. Allman, Mr. Brooks, and Mrs. Ford for giving me the tools to investigate and supporting my curiosity when maybe it was even a little bit out of control when I was a kid. So thank you.
I would like to thank two teachers, Mr. Troy Gehring, who inspired me in 5th grade to try new things, to push myself out of my comfort zone, and to Shannon Corton for bringing a love of math that then flowed over into science for me. Thank you both.
And I would like to thank my middle school science teacher, Mr. Sturlogson. He put up with a lot of strange curiosities and never once made any of us feel bad about that, and really encouraged us to dig into the things we were curious about, even if they seemed a little strange sometimes.
I would also like to remember and thank a couple of teachers that I had, one in chemistry, Sister Jeanette, actually, and one in mathematics, Mr. Brooker. And they taught me to love both mathematics and science, to keep going when things got challenging, and to be curious and be interested in all of the things that we were studying. So along with thanking our teachers, we also want to thank the many teachers that we work with across South Dakota. We have amazing teachers in South Dakota, and the things that we watch them do with students, and when we integrate with them, their effort, their persistence, their patience, all of that they do to inspire kids and get them curious about learning and keep them engaged. We're so thankful for that. And we would encourage each of you to think about a teacher that was impactful to you or your child, or someone in your community that's teaching, and reach out to them. It's February, it's the month of love. Show them a little love. Tell them thank you, and how much we appreciate all of the things that they're doing to help our kids be curious and love and create a love of learning. So with that, we will take some time for questions, if there are some questions. I'll invite the team back up.
Okay, yes, we do have some questions here. The first one, and this person has been waiting a long time to get their question answered. So I believe it's Nadim. Why should heat always flow from hot to cold and not the other way around?
That's a Peggy question.
Bring her into the camera.
The reason that it's flowing from hot to cold and not the other way around is because energy cannot be created. So you've got more energy in the heat. And so it can move someplace else, but you can't make energy in the cold that goes back.
Wonderful. Thank you. I've got a couple of other questions here, and this one kind of goes to the things you come up with, the way you create these curriculum modules and presentations for students. The question is, where do you come up with this phenomena? Essentially, where do you get these fantastic?
That's one thing when you sit down, phenomena are things that we all know, we see them. When we don't understand why they happen, that's what makes it a great phenomena. So when thinking about things for the units, we're trying to find things that we think that students will relate to, that they have hopefully a firsthand experience with. And when the phenomena comes from the kids themselves, that's the strongest phenomena we can have, because then we're actually answering their questions. So it's some trial and error, and we've had phenomena that have not worked, and we have some phenomena that work really, really well to help get kids asking questions.
And I think I can add to that. I think we all have that's strange list. So as we go through life, if we see something that is out of the ordinary or unusual, we collect those nuggets and we figure out the ones that are really complex, that have lots of pieces for kids to figure out, and we try to use those.
And we always try to find things that students can't easily search online themselves. So we want them to really dig in and explore the answers instead of just searching for them.
And I think one of the things you do is you ask students. You don't tell them the solutions to things. You try to develop ways for them to think about things critically and figure out answers for themselves. And how do you approach that idea?
It's definitely all about the figuring out, and that's exactly the phrase we use. We say that science is all about figuring out and not learning about. And so that's what we want them to ask the questions, and then even come up with the investigations that are going to help answer those questions if we can.
Great. Thank you, all of you, for those great answers. This is an interesting question. How do you keep on top of all of the science in order to share it with students in a way that they can really understand it? Because there's a lot of
We have a
science
great
out there.
communication department.
Well, we know that's not exactly how you find out information because your science teachers, your educators, you have to know a lot because you teach or you develop programming that covers a lot of the science, and not all of you are experts in these different areas. So what are some things that you might do to make sure that you're understanding the science so you can take that into the classroom and help students understand it?
One thing that I've noticed with our team, we take what we do and we try to do it really well. So it's always involves us questioning and investigating the things that we're trying to take to the kids. We have some big science projects that, we really try to anchor a lot of the things we do on, and we really work on those. But every time we interact with someone here at SURF, whether that's someone from engineering or someone that's in the science or somewhere, we get inspired. They do things that just amaze us. They show us phenomena, and we always have this working bank of stuff that's like, here's something else we could talk about. This is something we could do, and there's a lot of it. So it's hard to do it all, but it's fun, and that's what keeps the job really exciting.
And I'd say too that we have a love of learning ourselves. So we love learning, and we want to share that passion and that love with the students that we work with and the teachers that we work with.
Now, this question I just got, again from Nadim, who is new to this area. And it may be a question for another time, because I know if somebody were to ask me this question, I would have a very long answer because there's a lot to share. Tell us briefly about the history of surf and what kinds of research are done here.
I would suggest that they visit the visitor center and learn all about that, and then
Check out the website,
check out the website. Yeah.
sanfordlab.org.
Yes.
Great, because it will take, there's a lot to know. There's a lot of history here. I'm going to ask one more question. How cold does air have to be before water starts steaming or vaporizing? So if you've got warm water, like 70 degrees, how cold does the air have to be?
So actually, as soon as water turns into a liquid, based upon the air pressure, some of the particles on the surface are already drifting off into a vapor. That's why we don't see steam coming off lakes and rivers, but evaporation is what takes the moisture back to the clouds and creates the water cycle. So it's always happening. As soon as it's a liquid, we now have some vapor. As it gets hotter and has more energy, based upon the pressure, it just becomes a little bit more pronounced, and you can see it as steam or water vapor or fog or things like that.
Thank you. I don't see any other questions. So I want to give a big thank you to this amazing education and outreach team. SURF is very fortunate to have such a committed and dedicated group of people. And I also want to say thank you to Peggy for her many years of service. Woo! She has been a mainstay at SURF, and we have just been so fortunate to have learned from her over these past 13 years, and to be able to work with her and continue to discover and to learn more about some of her adventures that she's taken around the world to see eclipses and other wonderful phenomena. So I'm going to thank you, and then I've got some information. I've actually got a gift for our E&O team, but I think we left it in the other building, so you guys will find it out tomorrow. We're going to give you some fabulous swag from SURF. So if you haven't gotten any of the new cool stuff, so that's what you're going to be getting. I want to thank you all again for this fantastic presentation that you gave us tonight. It was a great learning experience. I need to thank also our Deep Talk sponsors again. I want to send a special thank you to the communications team. They make this, well, I'm part of that team, but I'm not running the show like Matt is. Adam is here taking pictures. Normally you see Erin here, and she does a lot of the planning for all of these different events. So I really need to give a big thank you to my team. I'm very fortunate to work with them. Now, I'd like to also remind you about next month's event, which is March 10th, Thursday, March 10th. It will be at the Historic Homestake Opera House in Leeds, South Dakota. And we are going to have an exhibit featuring film photography and oral histories from the people who worked at the Homestake Gold Mine. So watch for more information. It'll be coming out soon on our website and social media channels. And just another reminder, a recording of the talk will be shared on Facebook, as well as SURF's Vimeo and YouTube channels. So feel free to share all of those with any friends who have missed this live event, because this was really an educational thing. And when you leave the webinar tonight, take some time to do the survey about the Deep Talks experience. We really want to make these events better, especially the virtual ones. So please leave us some feedback and using that survey, and we will try to make some good changes for you. And thank you so much for joining us tonight. I look forward to seeing you next month at the Opera House.